Hi there, this is Astrophysics, this is Surveying the Stars Lesson 5, and this is Wien's Displacement Law. So here's a wide field image of the sky, night sky, including the Milky Way. Obviously, because we're in the Milky Way. Taken from Australia. What you can see is that there's lots of different colours of different stars. So you've got blue in there, you can see some red, orange, hint of white maybe. You can see some chromatic aberration on some of the images. So, right, let's see what it all means. So, starlight. Stars differ in colour as well as total brightness or power output. And colour differences are only really apparent when stars are viewed through a telescope, as telescopes obviously collect more light than the human eye. Stars obviously emit thermal radiation that is continuous across the electromagnetic spectrum. However, each star has a wavelength for which it emits at a maximum power. So in this case, the sun, this corresponds with a wavelength of yellow light. So the power variation versus wavelength follows the pattern of a black body radiator, and a black body radiator, or black body, is a perfect absorber and emitter of radiation. So next up is some black body radiation curves. So power radiated at each wavelength, so power is the amount of energy per second at each wavelength. So wavelengths in micrometers. And what you'll see, or should notice, is that as the peak wavelength is shifted to the right, so as peak wavelength increases, the temperature of the star goes down. So there's a relationship, an inverse relationship between peak wavelength and the temperature. And what some genius did, called Wien, is make a displacement law. And the wavelength at peak power, lambda max, is inversely proportional to the absolute temperature T of the surface of a black body, and you come up with this equation. So lambda max T, so peak wavelength times the temperature, is equal to a constant. And the constant is 0.029 meter Kelvin. So it's on your data sheet. And it's written like this. So lambda max T is equal to 0.0029. It is not milli, all right? It means meter Kelvin. So it don't mean millikelvin. So don't make that mistake. And the equation can be used to determine the temperature of the surface of a star known as the photosphere. All right, so let's look at different star colours and corresponding temperatures. So first one, star colour's red, surface temperature is about 3,500. Peak wavelength will be 830 nanometers infrared. So an example of that is Antares, which is a red giant. Star colour shifts to orange, surface temperature 4,300 Kelvin. So you notice that the peak wavelength has shifted and it's now shorter. So an example of that is Arcturus. Yellow, so getting hotter again, surface temperature 5,500 Kelvin. Wavelength shifting to be shorter again, so 530 nanometers, which is yellow. An example of that's Capella. White stars, surface temperature is increasing again, 7,500 Kelvin. Peak wavelength is 386 nanometers. Example of that's Altair. Blue stars, surface temperature even higher again, 20,000 Kelvin. Peak wavelength is curving at ultraviolet. Speak as an example. So essentially blue stars are hotter than red stars. All right, so don't think red is hot. So blue is, the hottest. Right, so let's do some questions. So we're going to use the Wien's displacement law, relatively straightforward, especially compared to the absolute magnitude questions that we did last lesson. So if you want to have a go at this one. So calculate the peak wavelength emitted by the sun if its surface temperature is 6,000 Kelvin. So we're going to apply the displacement law. So lambda max T equals 0.0029, 0.0029. And then simply rearrange. So wavelength, peak wavelength, 0.0029. Oh yeah, I forgot to mention, temperatures must be in Kelvin. Let's not fall into that trap if it gives you degrees Celsius. So peak wavelength, 4.83, times 10 to the power minus 7 meters, which corresponds obviously 483 nanometers. All right, let's do another one. So I'm going to pause and have a go at this one. So question 2. Red giant Betelgeuse, peak wavelength 828 nanometers, and blue supergiant Rigel, peak wavelength 263 nanometers, are both in the constellation of Orion. So what we're going to do is calculate the surface temperature of both these stars. So we're going to use lambda T equals 0.0029. And then just rearrange to find temperature. So for Betelgeuse, temperature 0.0029 divided by peak wavelength, so 828 times 10 to the power minus 9, gives us a surface temperature for the photosphere 3500 Kelvin. And then for Rigel, lambda T 0.0029. So the temperature 0.0029 divided by peak wavelength, which is 263 times 10 to the power minus 9. So photosphere temperature for Rigel is a whopping 11,000 Kelvin. So like I said, relatively straightforward. Just got one more to do. So this is really straightforward as well, but then I'm going to get some extra information after doing it. So we've got a very large black body. As a thermal temperature of 2.7 Kelvin, calculate its maximum power wavelength, so peak wavelength. So we're going to use Wien's displacement law, lambda T, 0.0029. So wavelength, 0.0029 divided by a very chilly 2.7 Kelvin. So that gives a peak wavelength of 0.0011 meters, or 1.1 millimeters. Now you might be wondering why this is significant. Bear with me a second. So this is the wavelength of microwaves. The very large black body is space, it's the universe itself. And this is cosmic microwave background radiation. And it was first detected by Penzias and Wilson in 1965, and is one of the main pieces of evidence that supports the Big Bang theory of the origin of the universe. Now it's linked to redshift, so obviously as the universe is expanding, light travels through the universe is also subject to that expansion, and light gets stretched, and it actually comes out of the visible region through the infrared and is actually stretched to become microwaves. So when you look at the, if you microwave detects into the sky, you'll detect microwaves, but also Wien's displacement law also corroborates the the microwaves being there at that thermal temperature, and it's just extra evidence to support Big Bang theory. Anyway, we found that useful, and thanks for watching.